Local linearity, an introduction to calculus. If I had to come up with a subtitle for this lesson, it would be this: Appearances can be deceiving. But this lesson serves as an introduction to calculus. Here's the graph of a function on a coordinate plane. We'll call this function function number 1. What is the algebraic function or formula for this graph? It looks like we have points at 0, 0 and at 1, 2. Between these 2 points we have a rise of 2 and a run of 1. So since our rise over run is 2 over 1, or 2, our function is y equals 2x. Let's take a look at the graph of function number 2, shown here. What is the function or formula for this graph? It looks like we have a horizontal line with a y-intercept of 2. So accordingly, we could say that this function looks like the equation y equals 2. Now let's look at one more function, function number 3. And again we ask the question, what is the function or formula for this graph? It looks like we have a y-intercept of -1. And it looks like the slope is about -2 over 3, or 2/3. Therefore, we say that the function is y equals -2/3 x minus 1. Here we are back to function number 1. We will next reveal the truth about function number 1. The real function is y equals the sine of 2x. How is this possible? This doesn't look like a sine function. Here's how it happened. Here's the function with the values given on the x and y axes. Note the very small numbers along the axes, 0.001 and so forth. And here's the function graphed in a standard window. So the close-in view doesn't show us what this function is really doing. Close up, this function looks like a line. This is an example of local linearity. Now let's take a look at function number 2, which looks to be y equals 2. The real function here is y equals x cubed plus 0.002. Here's the function y equals x cubed plus 0.002, this time seen in a standard window. The thing again making the difference in what this function looks like, the scale of the units in the coordinate plane. Up close, the function looks like a horizontal line. Viewed in a larger standard window, this function looks like y equals x cubed. But this view hides something else. The y-intercept is not 0, but 0.002. But here it looks like the y-intercept is 0. In order to see all the critical characteristics of a graph, we may need to use different windows or views. And finally, we'll take another look at function 3, which appears to be y equals -2/3 x minus 1. Here's a look at the real function, y equals -2/3 x minus 0.001. It looks like the y-intercept is -1, but in reality the y-intercept is -0.001, very close to 0. Here the function is viewed in a standard window, the y-intercept appearing to be 0. Note that between the two different views for this function we've seen, they both look like the slope is exactly what it really is, which is -2/3. There are many examples of the principle of local linearity in real life. When you look out at the ocean, like in this picture, the horizon appears to be linear. But we know that the reason we see the horizon as a line is based on how far away we are from it, which alters our perspective. Here on the right is the horizon from a distance, curved and appearing to be circular. When we zoom in on any point on most functions, the function will appear to be linear, even for functions 1 and 2 as shown here. In mathematics, up to calculus, we looked at objects that were stationary, not moving. Calculus examines precisely how things change. Calculus is a study of motion and change. Specifically with calculus, we can, in effect, zoom in infinitely and determine the exact slope of any point on a function. With any 2 points on a function, we can find an average rate of change. A line between any 2 points on a function is called a secant line. We can use 2 points on a secant line to find the slope of a secant line. The slope of a secant line is an average rate of change between these 2 points. We can look at one point on the graph of a function such as this point, and we can draw a tangent line, which is a line that touches the graph of a function at one point. And the slope of that tangent line is the slope of the function at that point, what we call the instantaneous rate of change. We can use algebra to find the slope of a secant line or average rate of change. And while we may estimate the slope of a tangent line, we need calculus to find the exact or precise slope of the tangent line or instantaneous rate of change. Let's look at one more example. We have a car that travels 50 miles in 1 hour. We start the car at time equals 0, and exactly 1 hour later the car is 50 miles away from where it started. Let's take a look at a coordinate plane. Here's a coordinate plane where we'll examine the situation. And here we have plotted on the coordinate plane the starting and ending points for the car. How did the car get from the start to the finish? There is an infinite number of possibilities. The car could theoretically have gone at the same rate or speed for the whole distance, and that constant rate is represented by a line connecting these 2 points. It's an average speed of 50 miles per hour, but we know from experience and common sense that a perfectly constant speed over any distance is realistically impossible. We could take the distances at any 2 points in time and use the data to determine the average speed between these 2 points. But with 2 points, we will always get an average speed and never an exact speed. And that average speed is the slope of the line between the 2 points. To get an exact speed, we will need not algebra, but calculus. Calculus can give us the equation of the tangent line at a point on a curve, and the slope of this green tangent line is the speed of the car at this exact time. You cannot use the algebra or algebraic methods of finding the exact slope of this line with 2 points, although by placing 2 points very close together, you can have a very close approximation. This has been Local Linearity, an introduction to calculus. Thanks for viewing.